book one, don't look at the answers. All right. Okay. All right. Okay. So we will start with complex number. That's the only thing I'm going to teach today. Today is just introduction. I don't want to stress you out too much, but just to give you a taste, and obviously you can go and read the lecture notes, start reading the book, textbook. The only reason I keep the old book is you can get that in May. It's a well-known book, used everywhere, but they have the new edition. I didn't use the new edition because, as you said, engineering students don't want to spend money. They want to hold on to their money. Anyway, so this book you can get in many ways. Just Google it. Okay. So what is a complex number? So I'm sure you know what is a complex number. Let me make it. Okay, good. Complex number. Usually we denote a complex number using a real axis. It's always easy to visualize like this imaginary axis. So if a complex number has a real part and an imaginary part, we write a plus jb. That is a general form of a complex number. Sat here is a complex number. Whereas a is a real number, b is a real number, but sat is a complex number because it is a plus jb, where j is square root of -1, which you all know it doesn't exist. But we use this, that's why it is imagined. It is not real. It is imagined, but using the imagination, we can model a lot of signals, and it is very useful, as you will realize throughout this course and even later, that that is where this complex concept of complex number starts. So sometime we can, if I have to plot this, I will plot it like the real axis, imaginary axis, and that is a, that is b. So this is sat is equal to a plus jb. So that is how I will plot this. So there sometimes we can express this number in polar form. So in polar form, we can write this function as this number in polar form. We can write it as sat is r theta. That's it. Two parameters. R is the distance. R is a square plus b square. Theta is the angle. Those two information is as good as a plus jb. A is the x-axis distance, b is the y-axis distance, and then the same can be, as you can see, said in polar form as r theta, where r is the a squared plus b squared, and theta is tan inverse b over a. So r and theta can be defined in terms of a and b. So r is a squared plus b squared, theta is tan inverse b over a. All right, so that's simple introduction to complex numbers. Now, this is most likely a review. I know that you guys took this course in math sometime in first year. So then this Euler's formula, we will use this many times. That's why I'm introducing here. E to the power j theta is cos theta plus j sine theta. You should know this always by heart. This should be in your memory. That's very useful formula. So, and then, so sat is a plus j b, and then here a is r cos theta, and then B is R sine theta. We saw that here. So, and then we can write that R cos theta plus J sine theta. So R times e to the power J theta. That is the polar representation, in exact terms. So that's the polar representation. Now, if you use this to expand this, R times e to the power J theta is cos theta plus J sine theta. We will be back to that original. So you should be able to convert a complex number from this to this. So that's probably the first example. Express sat is square root of 12 plus 2j in polar form. That's a question. I'm just writing down. So we have to write sat is equal to R e to the power j theta. Basically, we need to find, the question is basically find R and theta. So R is square root of a squared plus b squared. So that is a is square root of 12. A squared is 12. B is 2. B squared is 4. Square root of 12 plus 4. That is square root of 16. Which is 4. That is R. Theta is tan inverse B over A. B is 2. A is square root of 12. So that's going to be 2 over square root of 12. That can be simplified as 1 over square root of 3. So that is tan inverse 1 over square root of 3. So tan inverse 1 over square root of 3, we used to, that's, you will, if you look it up, you will see, and I'm sure many of you know that, for this important function, that is 30 degrees or 5 by 6. So we can write this in polar form. So polar form, that is here written, R e to the power j theta. R is 4, theta is pi by 6. R is 4, theta is pi by 6. That is a simple test of how this goes is going to go. So, and then don't think this is too easy. We will build on this. Everything that that we study will be being introduced. You can think, oh, I know this. I studied this before, because you're going to use it to understand signals. So just make sure you know everything. That's why there are 12 homeworks, because you have to review every time. Everything that is in my lecture notes will be used later. Okay, another example. Express sat is equal to 10 e to the power j. Sat is equal to 10 e to the power j pi by 4 in Cartesian form. So it's r cos theta, r sine theta. So this is r e to the power j theta. So in Cartesian form, that is r cos theta plus j r sine theta. So that's being done here. R is 10, cos pi by 4, j sine pi by 4. Cos pi by 4 and sine pi by 4 are 1 over square root of 2. So that is 10 over square root of 2 plus j 10 over square root of 2. When you simplify, it is 5 square root of 2 plus j 5 square root of 2. So that is that number. If I just draw that, that's going to be 5 square root of 2, 5 square root of 2, that is imaginary, that is real, and it's here. The angle is, so that is that number, angle is 45. That's all. Okay, a conjugate of a complex number. If sat is a plus jb, and then conjugate is a minus jb. We reverse the sign of the imaginary part. So let's make it. So that is sat. That is sat. that is sat is A plus JB, and then sat star, the conjugate, is A minus JB. So you can see, the B become negative. That is sat bar. And then in Cartesian form, you can write it as, if sat is R e to the power j theta, this will be R e to the power minus j theta. Why? If we use Euler's form, R cos theta minus, we will write plus R sine minus theta, that will be minus R j R sine theta. This will be R cos theta plus j R sine theta. So that is the conjugate of a complex number. That is a graphical representation. Now, complex number operations. If you addition is one of the operation. So to add, you will add the real part and imaginary part separately. So if you look at this example, A1 plus JB1, A2 plus JB2, SAT1 plus SAT2 is A1 plus A2, real parts added together, and the imaginary parts added together, A1, A2 plus JB1, B2. Multiplication. So A1 plus JB1 plus A2 plus JB2, you will just multiply like usual. So it will be A1, A2 plus J A1, B2 plus J A2, B1 plus J squared B1, B2. Now what is J squared? I don't know, what do you mean? J doesn't change at all? J squared is going to be negative 1. Why? J is square root of negative 1. It is clear? Okay, good. So this is going to be A1, A2 minus B1, B2, that is here, plus J times A1, B2 minus A2, B1. So that you see how the multiplication works. And then if you have, that's multiplication in polar form. So that's multiplication in polar form. That's even a little bit easier. Not easier, but yeah. So if SAT1 is R1 E J theta 1, SAT2 is R2 theta 2, SAT1 SAT2 is R1 R2 times E over J theta 1 theta 2. So the angles adds and the amplitudes R1 R2 multiplies. Special cases. So if SAT is A plus JB, SAT plus SAT bar is 2A. Now, SAT is A plus JB, not SAT bar, SAT star. So SAT is A plus JB, SAT star is A minus JB. So SAT plus SAT bar, SAT star, which is conjugate, SAT plus SAT conjugate is 2A. SAT times SAT conjugate is A plus JB times A minus JB, which is A squared plus B squared. Why? A plus JB, A minus A squared minus JB squared. So that is A squared minus J squared B squared. J squared is negative 1, so that's going to be A squared plus B squared. Yeah, not the notes. This is my lecture. It is from my lecture. So yes, you will get this. I will upload this right after class. Do you want it? Actually, I can upload it right now. Give me 1 second. Why it is not opening? Oh, it's here. Okay, so I was saying, okay, yeah, so SAT, the special case is SAT times SAT conjugate is going to be just A squared plus B squared. So that's the real number, SAT times SAT conjugate. Okay, so I also, you'll be doing a lot of MATLAB. So let me show you how I would type, a complex number in MATLAB. Let's say SAT is 2 plus 3. If you type J, you will just say 3J. In MATLAB, it says SAT is 2 plus 3J. And then to find SAT conjugate, we'll just say SAT, this transpose sign, that is 2 minus 3J. And then if you want to find the imaginary part of SAT, you will just type image SAT, it will return imaginary part. And if you want to know the real part of SAT, I will tell you it is 3. Let's say SAT1 is 2 plus 3. Okay. SAT2 is 4 plus 5 J. Then you want to, let's say you want to multiply them. So SAT3 is SAT1 times SAT2, and then it will give you the answers. We will be using, you can write I instead of J, that is correct. For example, SAT is 3 plus 4J without even multiplying. Yes, you can do that. Probably that's better. So you can do. So you'll be doing a lot of MATLAB. So in this time, and if you go to the lab section, there is a whole MATLAB introduction to MATLAB. The lab is based on that. So I would suggest, yes, in math, yes, it changes. Even though the question is, I put SAT is 3 plus 4I, but MATLAB change. Sorry, 3 plus 4. Even if the question is that I put 3 plus 4J, but it changes I. But that is a notation MATLAB uses. It always keep the complex number as I. Whereas in the lecture note, I'm using it J, but it's just a simple notation differences. But I will use MATLAB a lot, and unfortunately in the lecture note I'm using J, whereas in MATLAB it's just I. Other than that, they are the same. Okay, let's move on to another. Wait, you can't see this. I would prefer, when you write, I would prefer you use J. Yes, that's correct. Don't use, I mean, I cannot say it is wrong, but please, if you follow my lecture notes and the book, you naturally use J. So a sinusoid can be written, a general form, a sinusoidal signal can be written as the function ft is c cos 2 pi f t plus theta. So f is the frequency, theta is the phase, and then t is 1 over f, capital T, not small t. Small t is here. 1 over f is the period. So I will explain that. And then 2 pi f is called the angular frequency. So it is sometime angular frequency is measured in radians, RAD, radians, whereas a frequency is measured in hertz. So that's slightly different. So what is the difference? Frequency, we will usually use F. For angular frequency, we will use omega. Omega is 2 pi F. That's we can switch between the two. The only difference is the 2 pi there. The 2 pi in future, think about the angles. 2 pi is 300-degree angles. So a signal C is the amplitude. So if I plot this signal, where is that? Okay. If I plot this signal, first of all, let me plot the signal cos ft is sine 2 pi ft. Before I introduce C and theta, let's plot f is equal to sine 2 pi ft. So since it is sine theta, yeah, C, I'm going to answer what is C. It is amplitude, yes, but I'm going to elaborate on that. Wait a second. So the sine theta is going to be like this. So can someone tell what is this value? What is that value? This value, but that is 1. Yes. So when you C, if I multiply this by C, and then instead of 1, that is going to be C. That's amplitude. C. C can be any number. It can be 0.1 or it can be 20. Whatever you give, and then that signal will just scale to that amplitude. Now, but this won't change. If you multiply the signal by C, the period is not going to change. So what is the duration? So it's 1 cycle. What is the duration of 1 cycle? Using this notation, can someone tell me what is the duration? So that's t-axis. What is that? What should be here in this duration? F is a frequency, so that's going to be the time, the cyclic time, that is going to be 1 over f, because f is a frequency, right? Yeah. Okay, so in this signal, for the signal I showed here, I marked everything. Now, if I change sine to cos, technically all I have to do is move the axis, this axis here, because at t is equal to 0, cos 0 is 1. So it is shifted. It is shifted by 90 degree. So in other words, this phase theta, if I put theta is equal to 90, the sine become cos. That's the relationship between sine and cos. They are just sine and cos is in the phase. They are only 90 degree phase difference, 90 degree of pi by 2. So if when I say sinusoid, I call a sinusoid, and then I wrote it in cos, because it is all defined by the theta. It is a most general form. I can write either sine or cos, but it is written in cos. Or I'm just explaining why they are not that different. So if a general, very general sinusoid signal can be written using these parameters. So now you know what is C. C is the amplitude, and then F is the frequency, T is the axis. You compute it, it's a function of T. It is a function of T, because as with the time, it just keeps moving. And then theta is the phase difference. So everything that I explained here, that is shown in this diagram. So since in this plot, this is just this signal. Wait a second. So C ft is equal to C sine 2 pi f t plus theta is equal to 0. There is no phase difference because at 0 the signal starts like that. If there is a phase difference, then it will be like based on what of the phase difference. If it is positive or negative, based on that, it will start a little bit late, like that. So that is the phase difference. It's you can see this. This is the start of signals and system. We are starting to study about sinusoid, but we'll obviously go to study more complex signals. So now adding two sinusoid. So now I just gave a graphical explanation about a sinusoid. Now I'm going back. Now we will just stick to math, but you will always see the sinusoid can be thought of like this signal. Now I'm going to introduce a concept in sinusoid. Adding sinusoid. So let's say S1 is A cos omega 0 t, S2 is B sine omega 0 t, S1 plus S2 is A cos omega 0 t plus B sine omega 0 t. So then what you do, we do a little trick here, that what I do is I just divide both by multiply by square root of a squared plus b squared, and then divide by the same, so it remains the same, a squared plus b squared cos omega 0 t plus b over square root of a squared plus b squared sine omega 0 t. Why did we do that? If you just think about this, A, B, if this is A and B, let's say this is theta, we know that this is a squared plus b squared because this is 90 degrees. And then if I call this cos theta, if I call this cos alpha, and then this will be sine alpha, so that with that we can reduce this addition. We can reduce this addition into one single sinusoid. We had two sinusoids, but we used math to combine them into single one. So what changed? The amplitude changed and the phase changed. Important thing, the frequency did not change. So there's a question here. Express ft is equal to cos. My handwriting is not very good. I can still read it. 3 cos omega 0 t plus pi by 4 plus, is there a 4 or not? Sine omega 0 t. Sine omega 0 t, is it 4 omega? As a single sinusoid. I'm starting to wonder. There is no 4, okay? So that's what I see here. So that's going to be ft is 3 cos omega 0 t plus pi by 4 plus sine omega 0 t. I mean, if there's a 4, it's not a crime. You can still do it, but I'm just trying to make sure the answer matches the question here. So then 3 cos omega 0 cos, yeah, some steps were skipped. Cos pi by 4. What is cos pi by 4? 1 over square root of 2, right? Give me 1 second. So it looks like this answer. I will just redo it. Okay, probably I might have copied something. So the question is, ft is 3 cos omega 0 t. Oh no, omega 0 t plus pi by 4 plus 4. Oh, okay, it's right. It's right. So what I'm doing here is, first, this has, let's look at that. So that is 3 cos, we have to express the whole thing. There is no 4 here. So that's ft 3 cos omega 0 t, 3 cos omega 0 t plus pi by 4 plus sine omega 0 t. Because we have this pi by 4, we need to deal with that first. So 3 cos omega 0 t plus pi by 4. Let's expand that. So that's going to be 3 cos omega 0 t. No, cos a plus b is cos a cos b minus sine a sine b. So that is what's going here. Here what is happening is cos a plus b. We are using that expression is cos a cos b minus sine a sine b. That's what I'm doing here. So 3 stays there, cos omega 0 t cos pi by 4 minus 3 sine omega 0 t sine pi by 4. For cos and sine pi by 4, I can put 1 over square root of 2. So that becomes 3 over square root of 2 cos omega 0 t minus 3 over square root of 2 sine omega 3. And then this is this term sine omega 0 t. So the goal was to express this in a single. So now we have 3 terms. We need to combine all of these. So fortunately, this and this can be combined because these are both sine omega 0 t. So that is sine omega 0 t 1 minus 3 square root of 2 over 2. So that if you look at this, this is in the following form: a cos omega 0 t plus b sine omega 0 t, there where a is 3 square root of 2 over 2, and then which is 3 over square root of 2. B is 1 minus 3 square root of 2 over 2. So now we have A and B. So now we have to do the same. Now we the one simplification. Now we have to go back and write it as A squared plus B squared. Take it outside, A over that and B over that, and then you will design this as cos theta and sine theta, and you will find those. So I leave that for exercise. So that is the kind of thing we'll be doing in this class. You can see, you need to follow everything in real time. Otherwise, you might get lost really fast. So follow my lecture notes, and then hop on the book. And most of the homework assignments that I put will be from the book. I can already tell you. So this is, I want to stress again, this is your introduction to electrical engineering, your make or break in electrical engineering. So pay close attention to this course. So I will stop right there, and then you can just, I would suggest for the next lecture, I'm going to record it. Maybe I will complete this, and I will add some other examples, and I will upload this. So how this lecture is going to go: Monday we will be doing live. If you have any question to interact with me, we will do that way on Monday. For Wednesdays, I plan to upload recorded videos now. But I will constantly regardless, I will let you know what's going to happen. Well, for example, if there is a live class on Wednesday, I'm going to tell you in advance so that you can attend. And also, since I won't be teaching on live on Wednesday, I will also use Wednesday for the quizzes. So don't think that Wednesday will be a free time, because since the lecture is already recorded, I can use the time for a quiz. So then I can tell you all the quizzes are going to happen on Wednesday as well. So yeah, I'll stop right there, and then we will we will meet live on Monday. In the meantime, the remaining lecture notes, some lecture videos. Yes, there is a lab tomorrow. The lab is already there, and I can show you. Why don't I talk about the lab real quick? Let's go to Blackboard. And there's your Blackboard. If you go to labs, okay, so you are seeing my screen. So if you go to lab, that is your lab. Okay. In the last lecture, we stopped with looking at a sinusoidal signal. Today we are going to look at start with another type of signal, exponential signal. So usually we write an exponential signal as ft is equal to e to the power at or e to the power minus at. Let's start with e to the power minus at here. So ft is e to the power minus at. So let's plot this signal similar to how we plotted the sinusoid signal. So t is e to the power minus at. So when t is negative infinity, ft goes to infinity. So here t is negative infinity, ft goes to infinity. When t is equal to 0, ft is equal to 1. That is this point. And then when t goes to infinity, ft goes to 0. This is wrong. You have to correct it in the lecture notes. So that is this signal. So if t is negative infinity, you are infinity, cross at 1 and then go to 0. That is under the assumption that a should be greater than 0. Now on the right side we have ft is e to the power at. Once again it is given a is greater than 0. When t is negative infinity, ft is 0. When t is equal to 0, ft is 1. This point here, and when t is infinity, ft is infinity. That's this one. So then the function becomes this. So now I have a pretty good idea of how ft is equal to e to the power at or minus 8 looks. Now how about an example, that is sketch ft is 4 times e to the power minus 2t cos 12 pi t plus 90. So that is this question here. So we had to plot 4 times e to the power minus 2t. That's already plotted here instead of 1. It is an approximate sketch. Doesn't need to be to scale or anything. So that is 4 times e to the power minus 2t. And then now we need to plot cos 12 pi t plus 90. So if we write that in the form 12 pi t, our 12 pi t, if we write it in 2 pi ft format, that will be 2 pi 6 t. So that is the frequency. So the time will be 1 over f, so that will be 1 over 6. So that's why we have 1 over 6 2 over 6, 3 over 6. So that is the duration. That's the periodic time of the sine. So each of them is 1 over 6. Now you have basically multiply. So this amplitude is 1. So you have to just basically multiply this signal and this signal, and then the resulting signal will be, we will see the amplitude go up and high, and then gradually the amplitude will be reduced. The important thing is the periodic time won't change. The periodic time is going to be always, if we just look at these time, one period, second period, third period. I know this is what I'm drawing is not very up to scale, but always this is going to be 106. So that's, now we understand, we study in this section a signal that's a composite signal. That's a multiplication of two signals. So multiplication of e to the power 4 e to the power minus 2t. 4 is a constant that multiplies e to the power minus 2t, and then cos. And another thing I didn't show is cos 12pt plus 90. That's a phase shift. Usually cosine at 0 it starts like this. With plus 90 it will start with that. That is why it starts at 0. That is like sine. When t is equal to 0 function is 0, that is because even though it is cos, we have a 90-degree phase shift. That's why it starts here at 0. So you should be able to understand everything in this example. If I give a different example, you should be able to plot. I'm sure that there are many such questions in homework, and we will do some in the lab too, because as I said, this is the your door to electrical engineering, and I urge you to take your time to understand everything in this course, Signals and Systems. Now we are going to define two important definitions about signals. One is signal energy and the other one is signal power. So what is the energy of a signal? Energy of the signal is EF minus infinity to infinity f squared t dt. That is if it is a real signal. If it is a complex signal, it is minus infinity to infinity integration of f absolute value of ft squared dt from minus infinity to infinity. That's for complex signal. And then signal power, that is defined as a limit as t tends to infinity 1 over t, and then integration from minus t by 2 to t by 2 ft squared dt. I mean, if this complex signal, instead of ft squared, we will have the absolute value of ft squared. So what is t here? T is the periodic time. Well, sorry. I mean, it is not really periodic time, and that is a short definition. But we will do an example. It will make more sense in the example. So let's go into the example here. So we have a signal. The signal is ft. Ft is 2 e to the power minus t by 2, and then we want to compute the energy and then power of this signal. So let's do that. So by definition, energy of the signal is minus infinity to infinity ft squared t squared. So ft is 2 times e to the power minus t by 2. So ft squared is 4 times e to the power minus t. So that's what I have here, times dt. So 4 times e to the power minus t dt. Since important thing is in the definition it is given that t is greater than 0. So it is given in the definition t is greater than 0, so that we can change this limit. We change the limit from minus infinity to infinity to 0 to infinity because it was given that t is greater than 0. That means the signal does not exist when t is less than 0. So that's what we do. We just change the limit from 0 to infinity. So now it is just integration. You take 4 outside, and then integration of minus e to the minus t is minus e to the minus t, and then we will apply the limit from 0 to infinity. So when you apply the limit from 0 to infinity, e to the power minus infinity is 0, and then e to the power 0 is 1, so that's going to be just 1, so it is 4. So the energy of this signal is 1. In other words, it's basically we are integrating ft squared, so under this area. So ft squared is this. So if we just draw ft squared, it's going to be 4 times e to the minus t. It's a signal like this, and we are basically finding the area. Another way to look at it. So that area is 4. So this goes to 0. So that area that we are seeing here, that's 4. Now let's look at the power. So by definition, power is limit t tends to infinity 1 over t, integration from minus t by 2 to t by 2 ft squared dt. So ft squared dt, I wrote it 0 right away. Let me think. Minus infinity to, okay. So we can write this, up to this point it is the same. Up to this point the integration is going to be, so 1 over t minus t by 2 to t by 2 ft squared dt. I can write it as 1 over t 0 to t by 2 ft squared dt, because t is greater than 0. So then I can write it as 0 to t by 2 4 e to the minus t dt. So that will be 4 e to the minus t 0 to t by 2. Zero to t by 2. Okay, hang on. Then that will be 4 times e to the power minus t by 2 minus e to the power 0 1. Now don't forget that we have, after we compute the integration, we kind of ignore this and the limit. So let me bring them back. So it's going to be limit t goes to infinity, sorry, t tends to infinity 4 times 4 over t e to the power minus t by 2 minus 1. So now you can see this term, when t goes to infinity, that term is going to be e to the power minus e to the power minus, so that term is going to be 0 as t goes to infinity. So that the resultant is going to be limit t tends to infinity 4 over t times minus 1 really. So when limit t tends to infinity, 4 over t is 0, because 1 over t, that's basically, so that is going to be 0. So you should, I did not, in the lecture note I did not write it, but that explains why the power of the signal is 0. So we will get, let me do another example. The next example, after the next example, we will we will sit back and think, what is energy and what is what. These are two very important things. So we will call this type of signal an energy signal. This signal that we just worked on, e to the power minus t or e to the power t, these type of signals are called energy signals. It has a limit. It kind of makes sense. It has limited amount of energy. It all started with the definition that t does not exist when t is less than when t is less than 0, the signal does not exist. That's the energy of the signal. It goes down to 0, and it only has limited energy. So that's why it is called an energy signal. If a signal never stops, that's the next signal we are going to see, then it has infinite energy, limited but finite power. Whereas this signal has a finite energy and 0 power. So if you have a finite energy and 0 power, this is called an energy signal. We will later define this formally, but I'm just saying because since we just proved these things. So anyway, for this signal, we just proved that the energy is 4, where power is 0. So for this signal, energy is finite, a value, and then power is 0. Okay, now we are going to compute the energy and power of another signal shown here. This signal is a periodic signal, and unlike sine, this there's no closed form way to write this signal like sine t or cos t, but the picture tells the nature of the signal. It is from -1 to 1. It is like basically ft is equal to t, and then that signal repeats, goes back, and it's sometimes called a sawtooth signal. That is the signal between -1 and 1. It repeats. So let's compute the energy of the signal. So energy of the signal is minus infinity to infinity ft squared dt. That's the definition of the signal. So if you look at this, minus infinity to infinity ft squared, it is the same as computing this from -1 to 1, and then that is going to repeat infinite times. So from -1 to 1, ft squared is t squared, and then we have to basically we can compute that, and we don't really need to compute this. We see it is a finite value. Ft squared, the integration between -1 to 1 is a finite value, but the limit is infinity, so this is going to be, the answer is infinity. The energy of the signal is infinity. So remember how I explained the energy. So if this is ft, let me draw the ft squared of the function. Let's get some insights to why the energy is infinity for this signal. So ft squared, how it is going to look. So -1, 1, 2, 3, and so on. So ft squared is going to look something like like this, and then it's going to look something like this, right? T squared. That is ft squared. Now by integration we want to find the area under this ft squared integration, right? So that's the area. I'm just shading that. So if you integrate this area from minus infinity to infinity, that is infinity. So that's why the energy is infinity. Well, I can also say that you will all realize after we are done doing all the, I mean, maybe after we are done finishing lecture 1, which is one of the longest lectures in this, longest and important lectures. I will take at least 2 weeks to finish lecture 1 because it is very basic and very important. So anyway, at the end of the lecture, we will realize that periodic signal has infinite energy, and whereas this signal, it is it is not a periodic signal, and probably I did not formally define periodic signal, but we saw that in for example, sinusoid is a periodic signal, and a periodic time is the element of that signal that repeats. So this is a periodic signal. In this signal, which one repeats? If you look at the signal, this signal repeats all the time. That is a signal that repeats from -1 to 1, that signal. So if the signal goes from minus infinity to infinity, it has a periodic nature, then that signal has infinite energy. To contrast this, this signal, even though this this signal. Now, if you look at this signal is not periodic. This signal is not periodic. I mean, it has a period that yes, I said that it has a period, but the signal is not identical in each period. The amplitude of the signal dies with time. If you look at it, the amplitude gradually, the amplitude goes down. If I draw the envelope, the amplitude goes down to eventually 0. So that is not, it has a periodic nature. It goes up and down, and it has even a period like the sinusoid above it. It has a 1/6. It's when it crosses zeros, that's all fine, but it is not a periodic. It is not a standard periodic signal where nothing repeats here. This signal in the first period, this signal is not the same as the other one, except for the time on the t-axis. The y-axis is not the same. Whereas a periodic signal, if you look at it, that is the same signal. Nothing is changing. It's just that if you can just pick one signal from one period and put it on the other period, it's going to be the same. So to summarize, a periodic signal with a limited time duration like this one has zero power, yes, power is 0, and finite energy. A periodic signal like this has infinite energy. Let's see what is the power. The power of the signal is defined as limit t tends to infinity 1 over t by 2 over my integration of from minus t by 2 t by 2 ft squared dt. That's the definition of power. We saw that. So let's integrate this. So since so what we are going to do is we are going to set if you think about it, I'm going to set t is equal to t by 2 is equal to 1. So we will say t by 2 is equal to 1. So that's how we are going to do this, and I will explain why. So then t, that's going to be t is equal to 2. So the integration part, except for the limit, is 1 over 2 1 to -1 f t squared dt and then ft is t, so that's going to be half minus 1 to 1 t squared dt, and then that's going to be half, I'm basically repeating what I wrote in the lecture notes, t cube over cube 1 to negative 1. Now that is going to be 1 over 3 minus 1 over 3, so half 2 over 3, so that's going to be 1 over 3. Now I did this without this limit t tends to infinity part. Now I'm going to argue why it's going to be the same. We did this for one period. If I select, so I selected one period and did that. If I select, so let me draw that. So this is where I did the integration. Let's say I double it and do the integration here. It's going to be the same. The value that we are going to get is going to be the same due to symmetry. So let's add 2 more, and every time I do this, it's going to be the same, because when I expand the time duration, the t that divides is going to be proportionally the same, so the answer is going to be the same. So that's one argument. But since it is a periodic signal, you can forget about that logical argument, and you can just I'm going to now say that. Earlier I almost said it but did not say it. Now we can say always select t as a period, signal period. So in this signal, t is equal to 2. T is equal to, that's the period of the signal, and we will do the integration from t by 2 to negative t by 2, because I already made the argument here that we don't need to do it for infinity, and we need to apply for the limit of infinity. We can just do it for the t by 2 and negative t by 2 and not apply the infinity, because there's no need to do that. So that's logic behind why we are doing that. Anyway, this is for this periodic signal. We just found out that the energy of this signal is infinity. The power of the signal in this case is 1/3. The most importantly, power is finite. Power is finite, energy is infinity for this periodic signal. Okay, we are going to do another example. Here we are going to find the power. We are going to find the power of a sinusoid. So let's find the power of a sinusoid. It can be any sinusoid, but I define that sinusoid as a cos theta t. A cos theta t. So we are going to find the power of this signal. And if I ask what is the energy of the signal, you would say it is infinity, because we just saw that in the previous slide, that since this is a cos theta t, it is an periodic signal. The energy for a periodic signal, we proved it for us given example that the energy is infinity. You can do the same approach to prove again that for this one also the energy is going to be infinity. So we're not going to bother proving it again. Now it is a given that since it is a periodic signal, energy infinity. So, and we also know that the power is finite. What is that power? That's what we are going to find out. So once again, I am writing the definition here. The definition is power is limit t tends to infinity 1 over t, integration from minus t by 2 to t by 2, ft squared. Ft is a cos t, so ft squared is a squared cos squared theta t dt. So cos squared, you cannot integrate cos squared theta t, so we had to use this nice relationship, one of these trigonometric relationships, that cos theta t is half plus half cos theta 2 theta t. That is one of the trigonometric identities that you will need for this derivation. So once you use that, you will substitute instead of this half plus half cos theta t. So that divides the integration into two. The first part here and the second part here. The first part is you take a squared by 2 outside, and it goes to limit t infinity tends to infinity 1 over t integration minus t by 2 to t by 2 dt. That's going to be limit t goes to infinity 1 over t times t. So that's 1. So that's just a squared by 2. And what about the other half? That is, you have a periodic cosine signal that if you integrate it, this signal, periodic signal, it is top half is positive, the other half is negative, so it's going to be always 0. I mean, you can imagine this way, or as I said earlier, you don't need to worry about it. You have to just apply the limit within this region, and then you don't really need to worry about this limit. That's another way to look at it. When you have to do the power of a periodic signal, you will just do it 1 over t minus t by 2 integration, and you can kind of forget this limit part, because it's going to be it's not going to matter, because we all understood it. So anyway, so power of this signal a cos theta is a squared by 2, and then it is a very important derivation I just did. So let me add a few insights that any signal, you can test this. Let's say ft is a, this might be a quiz question. I gave this question many times as a quiz, and most of the time students will struggle, cos, for example, 2 pi t plus phi, and then I will ask the students to derive what is the power of this signal. Students will do all kinds of integration, and most of the time they won't get the answer, but you can close your eyes and write the power of this signal is a squared by 2. That is something you need to know by heart. So you have a just think about an AC power, AC signal, AC DC signals. AC signal, that's the one that powers our homes and everything. So you have some AC signal. If you go and work at NWIN for internship, for example, you have an AC signal with amplitude, I don't know, 50 volt, and then whatever the period is, and what is the power of the signal, what is the RMS power of the signal, you will write it is amplitude 50, that will be 50 squared by 2. That's the power of the signal. So that's where it is coming from. It is coming from here. It is coming from this definition that we just studied. Particularly, it is coming from here. That is how we compute the power of an AC signal. Okay, now we are shifting gears to a different, not different, we are going to learn more about different types of signals. So we saw energy versus power signal, and what are other types of, this versus that in signal. Okay, then one of them is continuous time versus discrete time signal. So that's so what is a continuous time versus discrete time signal? The example is here. If you just consider x-axis as time, and then for every time value you have a y-axis. For every time there is a signal, that is a continuous time signal. Discrete time signal is, signal is discrete. Sometimes there is signal present, otherwise there is no signal. Sometimes it is present, sometimes it doesn't. Sounds familiar? The digital signal, for example, it sends signals as a pulse, 1 and 0, something like that. We have a special name for that as an analog versus digital signal. So that's and continuous versus discrete are kind of related, but we call it analog versus digital for that kind of signal. So analog is, a sinusoid is a very good example of an analog signal. It's always present, whereas a digital signal is something digital, that is either it is present or either it doesn't. It is not present, it is not. 0, 1, that is a digital signal. And then periodic versus aperiodic signal. So periodic signal, we saw that in the previous example. For example, cosine, sine, that is a periodic signal. And aperiodic signal is something, for example, if you have an exponential, exponential function, that is a periodic signal. Energy versus power signal. We saw that what is energy. We have seen many energy signal, like especially the exponential signal itself, that is an energy signal, whereas power signal is a periodic signal once again. So these are the different, this versus that. For mostly, if you look at it, mostly it's for periodic and energy type of signal. And then deterministic versus probabilistic signal. So deterministic signal, for example, if you think about RC circuit, which we will do in the lab, think about if we apply a voltage across RC circuit, and then we can determine that how the voltage is going to rise across the capacitor. It is basically like what is shown here. It will just gradually, we can estimate how the signal is going to rise. Whereas a probabilistic signal is some, for example, some statistical noise. Sometimes we can only define a signal. We can say on average the mean of the signal will be this, standard deviation will be this, but not beyond that, because it is random. Sometimes there is a random nature, that unpredictability. We cannot predict how it is going to be with time. Then that is a probabilistic signal. So those are different ways of categorizing signals. Now there are some signal operations. So there are 4 types of signal operations, 3 important ones: time shifting, time scaling, time inversion, and then a combined mean, combination of all of these. So first, time shifting property, that if you have a signal ft here, so that's the signal ft, and then ft minus 1 means the signal shifts by the same signal, but it's shifted right by 1. And ft plus 1 here means the signal shifted to the left. So if t minus k means it shifted towards k time, k distance to the right. T plus k means it shifts to the left by that amount. Time scaling, once again, if this is ft signal, that spans from time t1 to t2, and then f2t means it shrinks, the x-axis shrinks, but the important thing is the y-axis is not going to shrink. It's going to be whatever the value we had. Let's say it is 1, that's going to be the same. And then ft by 2, here it will just expand on the x-axis. So that's the time scaling property of a signal. And then time inverse. So if you have this as your ft, and then f minus t, if you just take this as a mirror, how the signal will look on the mirror, I mean, not exactly, I'm not, you had to, if the mirror means, this is a signal, and then you see the mirror here, it just reverses the signal. For example, if you have a signal like this, and this is the axis, and then it's going to be like this. This distance is the same, the height here is the same, everything is the same, but it's like a mirror image. That's f minus t. So that's a time inverse property. So we saw 3 properties: time shifting, time scaling, and time inverse. Okay, here's an example for this combined all signal operations. So we have a signal. Consider ft is a signal shown here. So it is defined as ft is equal to 1 between t 0 and 1, and it is 0 anywhere else. And find phi t, which is given by this, that is 0.5 f half t minus 3. So how do we find it? Then we operate one by one. First we find what is 0.5 ft. 0.5 ft just 1 become 0.5, and then what is 0.5 f t by 2, that is time scaling property, so it's t by 2 time scaling property, that's 0.5 f, just the x-axis expands, and then 0.5 t minus 3, and we saw that it just shifts, so it shifts by 3. So from here it shifted 3 position and then it became this signal. So that's the example of how to apply different signal, these 3 signal operations. That's another potential questions in quizzes and exam. I'll be giving a couple of questions in the homework. I think the homework is already up, but otherwise it will be up soon. You can start to practice this. And I would always suggest to seek the help book, textbook, to get more help. Right, that's it for the lecture on Wednesday, and then we will finish this lecture on good morning. Thank you. All right, can you hear me? Someone confirm the microphones. Thanks. Let me open the lecture notes and we can start. Open the lecture notes. MATLAB. Okay, you should see my lecture notes on the screen now. Yes, you can see my entire screen. Good. So there's one announcement. I think the lab is due today. A lot of you asked for, where to find these files. Always at the lecture notes, in my lecture notes, in the future lecture notes, all the necessary links. You will just see it under my name. For example, the link to the lab video. You just click this. It will go to somewhere. It will play a video from my Dropbox folder. You can download this video. I'm planning to upload this to YouTube. But it takes some time, so I just it is available. That's the important thing. The other thing is the files for the lab. I know I got a lot of emails, but if you just click on the link, the MATLAB files, Excel file, RCS, always this is the place where I look for. In my lecture notes, you will look for the videos, the files, and all those things. Also, I think the lab is due today. I don't know if you got this already. The time is over. What I want to say is this lab seems a little bit too big. And the reason I introduced this lab is to get you familiarized with MATLAB. You all are good in programming, either from my course last semester or taking the engineering software fundamentals. So we'll be using a lot of MATLAB in this course. And then since we are not going to the actual lab, one of the lab that is required for this signal course is also going to be done in MATLAB. That's why I thought of giving you a second lab about this, this circuit. So basically, our course requirement to implement these circuits in physically. Take a resistor as a capacitor, connect it to a power supply, and measure the rise time. And what is the rise time? All of that will be studied, will be covered in the lectures. So since we won't be going to the lab, I wanted to do that experiment in MATLAB Simscape. That's why I'm introducing Simscape. But then some of you are not familiar with MATLAB, so I just wrote a whole tutorial about MATLAB and Simscape. And then probably that's too much for lab one. That's why I said don't do the last circuit. Last example, which I'm going to create a new lab where we will understand a bit more about Simscape, and then we will do an experiment. Basically, you will implement this with the complete understanding of what you are seeing, the theory which will be taught eventually in this signals and systems. So always what I want to say is, before you ask me, which as I said, I have 300 students this time, my response will be delayed. Or you should ask the lead GA always first. Mostly you will get the answer from her. Otherwise, you can ask me. But before you ask, look here. For the lecture notes also, we're just starting, but the lecture notes also, you will see a link to the lecture video after the fact, because I'm recording them. All right. What is that? How much of the homework should we be able to do by the end of the class? What do you mean? You mean, are you talking about homework one? Let's see, homework one. Homework one. All of these today I'm finishing the lecture. So okay, let's go back to the lecture. I want to finish it today. So once I'm done with the lecture, you should be able to do all these questions, all 17 questions. All right. Okay, let's go to the lecture then. My goal is to finish the lecture today. And then one more announcement. There will be a quiz on Tuesday. I don't know, probably you got an email from GA already. So there's a quiz on Wednesday. So when you come to the class on Wednesday, there'll be a quiz at 10. you will have like 20 minutes to start the quiz. If you're late by until you can start the quiz until 10:20, and then you can take 20 minutes to finish. So 10 to 10:40 is a quiz. So there won't be a live lecture. Usually there won't be a live lecture on Wednesdays. I will have recordings uploaded. So now on Wednesday it's supposed to be second lecture. So since there's a quiz, you might not see a recording on the quiz as well. Oh, there will be only quiz for Wednesday. The quiz, okay, two questions. What is covered in the quiz? This is about everything that you did in this lab one. Where is that? Lab tutorial. Just it's about, this quiz is about MATLAB. This is what you were doing in lab one. You were just studying about MATLAB's command, all the arithmetic operation, all of that. So from example 1 to example 19, obviously you don't need to do Simulink. I'm going to postpone Simulink for a while. So up to example 19, that is what quiz is going to cover. You have 20 minutes, whatever you can practice in MATLAB, do it. This is a quiz about MATLAB. So that is what you will have on Wednesday. And then Monday, we will start with lecture 2. So that's all for the announcement. You saw a video that I uploaded for the last Wednesday part. So I kind of covered two inversions are extra more example. Well, is that true? I thought the $99 version has everything. It has Simulink and Simscape. That's what our technician told me. Yeah, see, somebody's saying that Simscape is included, because I got this information from our lab technician, Mark. And if you are really thinking that you just paid $99 and did not get a Simscape, send me that information. I can forward to Mac, because it is supposed to be there. So let's forward that your information. Send me an email with you saying how did you purchase, what is the link that you went to, and those details. I will ask, forward it to Mark and see what happened. They told me that $99 version includes Simulink. So I don't know whether you had, maybe there's a way. For some people it worked, but send me an email. We will figure it out. Any other questions? Yeah, how to download MATLAB and all those informations are here in this tutorial. Everything we put here, accessing MATLAB, how to download, all of that is here. So just go through this tutorial and you have all the details. Okay, what I want to say was on the quiz on Wednesday will cover. I think I already said that. MATLAB. Great. Okay, let's get back to business. So I talked about signal, and important thing. Probably I said it in my video, but I will say it again. Signal energy and power are two important things. You will, what is an energy signal? You need to know. What is a power signal? You need to know. Energy signal is a signal that dies down after some time. For example, here's two good examples. Like if you have a signal like this, it goes from plus infinity to negative infinity. That is not an energy signal, because that's that has infinite energy. But this is an energy signal. Eventually, the ft squared, integration of ft squared is a limited number, whereas power signal, and then this is an energy signal, because if you look at it, even though it has big amplitude at start and then it dies down, but power signal is a periodic signal. It just keep on going, sinusoid with the same amplitude goes all or on. That is the power signal. And we saw how to compute the power of a sinusoid signal. Very important. As the power of a sinusoid. Did I do that in the class? Yeah. So that's the power of a sinusoid. And if you look at this, it is a squared by 2, regardless of the phase. So if you are given a signal, xt is equal to a cos omega t plus phi, regardless of, that's a tricky question. I always like to ask. So I will ask you to compute the power of this signal. People will do all kinds of integration, and then some of them will exactly derive it to be a squared by 2. Some of them won't. But knowing answers sometimes will help you. But that is the answer. But sometimes I will ask for the step. You need to know how to do the integration as well. Would a radio wave emitted from a tower be considered energy signal? No, it's not energy. It's a power signal. Why? So what do they transmit from a radio from a tower? They send signal like they send signal like this. Mostly it is sinusoid. There are two types of transmission. One is analog, very rare, but it is still there. The other one is digital. If you just turn on your radio, there is AM and FM. FM is frequency modulation. AM is analog amplitude modulation. AM radio is always analog. One of the advantage of AM radio is it can travel really far, high distances. But nowadays there is digital transmission. So digital transmission is what they transmit will be zeros and one. So that's for that also, since it is repeating, it is cyclic periodic signal. So that's a power signal. So always that will be considered as a power signal. So I talked about classifications of signals. I think you are not seeing my video, right? Yep. Okay. Yeah, let me see if I can see both. All right. So yeah, you can see my screen and I can see a chat. Good. So he talked about the classification of signal in the video. Is there? I'm going to combine all this video and put it at the top of my lecture note file, so that when you're reviewing, you will have the video. Time shifting operation. We saw what is time shifting. For example, f t minus some delay, it just shifts the signal to the right. When we are looking right to my right when I'm seeing on the plane. And then time scaling. Time scaling is f t by 2. If you look at this picture here, f t by 2 is just spreads the signal. And then so f t by a, if a is greater than 1, spreads the signal. If it is a less than 1, it shrinks it. And the time inverse is, if this is ft, f minus t is a mirror. If this is a mirror, the signal just mirrors on the other side. So that's 3 important things, signal operation. And using those 3, you can just do a lot of signal manipulation. There are a lot of practice questions in the homework. Do it, then you will get a good handle in these concepts. Time shifting, time scaling, scaling, and time inversion. When we study about no, it doesn't matter which order you do this. Can any function be a signal? Yes. Any function could be a signal, but end of the day, what any function could be a signal, but end of the day, what kind of signal we will focus on? We are just walking you towards some of the most dominant applications in electrical engineering, like communication. So what type of signals are used in communications? What kind of signals will be considered in this class? That will be useful for you to later understand communication, which you will take next class. So that's the kind of signal. So we will spend a lot of time talking about sinc function. For example, you will see sinc function is a function like that. It starts like this and it dies down. If I drew the envelope, it will be like this, 0, and that's a very important signal in communication. So we study about it a lot. So it's like that. We will we will study about signals that are practical, that are useful to understand the real world. That's the type of signal that we'll be using studying in this class. Okay. Now we want to study about 3 important type of signals. So you asked a question about what type of signals can any function be a signal? Yes, but we are going to spend time studying about some important signal to understand electrical engineering principles. One is a unit step function. The other one is a unit impulse function. The third one is an exponential function. These are all very useful later, not even in this course, even other courses that will build upon signals. So unit step function is defined as ut is 1 when t is greater than or equal to 0, and it is 0 when t is less than or equal to 0. So this is sorry, this is t. So when t is less than 0, so that's 0 obviously. When t is less than 0, this function is 0. I'm going by the definition. When t is 0, it goes right away to 1. So that's transition there, right there is like instantaneous. Instantaneously transfers from 0 to 1. I'll be back. I have a coughing problem. I'll be back. All right. Okay. Yeah, that's my gaming system. Look at this. So when I'm back teaching, I play games. How about that? Okay. So the unit step function, if we apply these, can be used to express as a pulse. Okay, yeah. So I used unit step function and the signal operations that we studied earlier to define this pulse phi. Let me highlight this pulse. Look at this pulse. Now that's a pulse. Signals. Now pulse is very important when it comes to discrete signals. Like this is a pulse. It starts at 2, shoots up. So this is 1. So this is a signal phi t. And then 1. Okay, how do we write this? So what is phi t? You can write the answer there. So 2, 4. So if you just think about this, so ut, if I just shift u by 2, so ut minus 2 is that signal that you are seeing there. And then ut minus 4 is again a unit step function divided by 4. Now subtract one from the other, then you get this pulse. So this pulse is ut minus 2 minus ut minus 4. That's that pulse. Now look at another example. Look at another signal that I am showing there, that triangular signal just goes in a ramp, stops at t is equal to 2, and then comes back to 0 at t is equal to 3. How can we define this function using unit step function only? Let's add a page here. Okay, so let's separate this signal into two, part one, part two. So let's define each of these parts using unit step function. So the part one is if it is, let's see what t times ut is going to look. How t times ut is going to look. Ut is 1. This is ut. What about y is equal to t? Y is equal to t is this t. Y is equal to t. Y is equal to t is that, no, just 45-degree ramp. Now t. So tut, if I want, actually the proper way to write the second signal is tut. Why? Why it is not just t? Somebody can answer. Why it is not just t? That's the second function I am writing. Why it is just tut? It's because if y is equal to t, 0 less than, yes, because the function, if y is equal to t, then it will be like this. That is technically y is equal to t means for all y's of t, because now the ut function helps us to define a function yt that only exists when t is greater than 0. So the second function is just tut. So then only we can say there's a confidence. So this is tut. Now, but we want that function to stop and come back to, we don't want that function to exist after t is equal to 2. We don't want that function to exist after t is equal to 2. So what we really want is this. So how do we write that function? So how can I define a function? So that would be, this function in blue is yt is te ut minus ut minus 2. Because ut minus 2 is just 1, ut minus 2. Let me write that in green. This is 1. That green is ut minus 2. I just explained why earlier. So then you multiply by t, that is that function. So this function in green is t times ut minus 2. Okay. Now, what is the other function? So now we know the drill. So I need to multiply something by ut minus 2 minus ut minus 3. Something, let's call it ft. We need to find that ft. So that is the second function. So it goes down, and then, you know, I just found the mask. This is the mask that we want to apply. 1 and then t minus 2 to 3. That is the pulse. We're going to multiply that pulse. Now the remaining task for me is to find the equation of this straight line. Now, it's not very hard to find the equation of the straight line because we know 2 points, 1 point, 2 points in that line. So we can find the equation. So the equation is what the equation of this, and I did a small handwork there to do that. So equation, you know, since we had 2 points, you can find it. It is y is equal to minus 2t plus 6. So that is that equation. This equation. So ft right there is minus 2t plus 6 times ut minus 2 minus ut minus 3. So to summarize the signal, this signal 2 and 3, this signal, let's call it phi t, can be expressed as the first part is t times ut minus ut minus 2. The second part is minus 2t plus 6 times ut minus 2 minus ut minus 3. So that's how we just studied about a function. Okay, so how did we get minus 2t plus 6? So that is minus 2t plus, this is, if you look at this function in green, this function is y is equal to minus 2t plus 6. So if you don't know how to do that, I can do it here. So let me put all the details that we know that function. So it is at 2. This is y is equal to t. So this value is also, this value is also 2. And then this is 3. So we have two coordinates. One is 2, 2. Other one is 3, 3, 0. 3, 0. So we want to find the equation of this line that goes through 2, 2 and 3, 0. How do we do that? So for one, we know that the equation can be written as y is equal to, there are many ways to do this, mx plus c. That's a general equation for a straight line. So we know 2 points. One is 2, 2. So let's apply those points. So applying 2, 2 here, 2 is equal to m times 2, 2m plus c. I have one equation. Second, we have 3, 0. 3, 0, applying 3, 0. So 0 is equal to 3m, 3m plus c. So that's equation 1 and equation 2. We have basically solved this. So if I subtract from 2 minus 1, you will get minus 2 is equal to m. So from this, I have one answer, m is equal to minus 2. And then substitute m is equal to minus 2 in 2. There we go, that's easy. So 0 is equal to minus 6 plus c. So c is equal to 6. So I have m is equal to negative 2 and c is equal to 6. So the equation is y is equal to m is minus 2x plus c. I'm going to change instead of x because our axis is t, and I should have used t all along because we are very used to x, using x for x axis anyway. So this equation is actually substitute x t, that's going to be y is equal to minus 2t plus 6. So that is how we came to find this equation. That is the equation. So to again put that in perspective, this equation there is minus 2t plus 6. But we only need that in that area, that 2 to 3 range. So this is right there. That is u t minus 2 minus u t minus 3. Very important, this height here is just 1. That is why when we multiply, nothing changes. For example, if ut is defined as like forever a, it has an amplitude a, then it would have been a problem. But since a is equal to 1, when you multiply, it remains the same. The ut, that pulse is used to mask that minus 2t plus 6 for the region where we don't want it. So I hope that explains it, and you make sure you understand this well. There are many questions like this in the homework. So yeah, you need to understand this to do the homework. So basically what we did, we used a unit step function to explain signals. First, we used a unit step function to explain a signal like this, and then we used unit step function to explain a signal like that. Okay, now we are going to study about another important function. This is called unit impulse function. So unit impulse function, if you ask me to draw it, I will draw it like this. It's like with an arrow. So this is t, that's t is equal to 0. So I mean, I'm just going to draw an arrow and then write. There's some effort needed to understand this function. So first, like how we define unit step function, we define unit step function as ut is 1 when t is greater than or equal to 0, 0 when else, or when t is less than 0. So that is how we define unit step function. So we want to do more than just draw a signal. We want to define it mathematically. So this is how unit impulse function is defined mathematically. That is delta t is equal to 0 if t is not equal to 0. Whenever t is not equal to 0, delta t is 0. So then the next thing is minus infinity to infinity delta t times dt is equal to 1. The important thing you need to note here is I did not say what is delta t at t is equal to 0 because it was done on purpose. So we are not saying what is the value of delta t when t is equal to 0, because everywhere else when t is not equal to 0, delta t is 0. So when t is equal to 0, it should be something, we can say it, but rather than that, it is defined such that from minus infinity to infinity, minus infinity to infinity, delta t dt is equal to 1. If you think about it, from instead of writing minus infinity to infinity, I can say, because t doesn't, delta t doesn't exist for any other values of t except t is equal to 0. So that's why it is a slightly tricky definition for delta t. So you should bear that in mind. But we won't be stuck with the definition. There's so many ways where we will, the next properties will help, and then you will see. I will refer to this portion of this lecture many times in the future, that this delta t function and these two properties that we are going to talk about are going to be used over and over again. So anyway, so there are many ways to define this, kind of explain this unit impulse function. One of them, so in a crude way, you can say, sometimes we will, some books also even say, it will say delta t is equal to 1 when t is equal to 0. Not very pretty, but just sometimes we define it. But what is proper is to define this in one of these 4 ways. So if you just think about it, it is delta t is 0 when t is not 0. All places of 0 it is 0, and the integration of delta t is 1. That means delta t should be 0, 1. It should be 1 at this place. That's the argument for writing like this. But there are many other ways to write it. One of them is, if you just consider a function like this, consider unit, no, not a unit step function, like a square function like this. Now that function from minus epsilon 2 to epsilon 2 is the amplitude or height of the function is 1 over epsilon. So what is the area? If you just think about it, the area is 1. So area is 1. Now, Now, do you define a function with that epsilon like that? Now, when epsilon goes to 0, it will become smaller and smaller and smaller. Now, if the epsilon becomes smaller and smaller, what will be the height? Any guess? This height, 1 over epsilon. So when epsilon goes smaller and smaller, what will happen to 1 over epsilon? It will go to infinity. So that's why sometimes, the proper way to write, if I want to draw delta function, putting 1 delta is equal to 1 is kind of wrong. So actually, that's why we put an arrow to explain delta function. That means, it goes to infinity. When t gets to 0, that's probably a better way to, rather, that's why putting delta is equal to 1 is problematic. But you will see, assuming so, will work in many practical applications. Now, second way to explain delta function, consider a situation like this. So consider function alpha e to the power minus alpha t. So I'm wondering, so that's only considered for t is greater than 0. I will hold on that. I thought that there should be a ut there. Anyway, I'll go to the next one. Consider a function like this. Epsilon is a triangle function, and then the area of this function is also 1. Now it's epsilon here, minus epsilon here, and this height is 1 over epsilon. The height of this triangle is 1. When epsilon goes to 0, that's very, very similar to that explanation. The first explanation. Then when epsilons go to 0, this will become a unit step function. And the other one is the Gaussian function. The standard Gaussian function, ft is written as 1 over square root of 2 pi sigma e to the minus t squared over 2 sigma squared. Instead of sigma, we are going to use epsilon. So I'm going to rewrite it 1 over 2 pi epsilon e to the power minus 2 squared over 2 epsilon squared. Yeah. This will be useful in ADC too, yes. But I'm not. I don't think analog to digital conversion is covered, even though I will talk about it about this analog to digital conversion later. Yeah, and actually we have some. It will be covered to some extent. So the Gaussian signal is it's a signal like this. The well-known feature of the Gaussian signal is it is used to describe probability. It's called bell curve. It has many names. Gaussian normal distribution, standard normal distribution. All of that is this function. The important thing is the area under this is 1, which is well known. So this area is 1, and then when the standard deviation, or in this case epsilon, becomes smaller, it will approach like this. So which means again, when epsilon goes to 0, it becomes an impulse function. For this function, I think in my definition I'm missing something, so I will just skip it. Maybe I will fix it later. Because e to the minus alpha t there must be something else to tell that the function is not defined, unless it is defined this way, like with the absolute value. Yeah, I'll think about it later, and I will fix the next lecture notes. Okay. Anyway, we studied about at least three different ways to properly define an impulse function. One is this, other one is this, other one is this. 3 different ways an impulse function can be defined. So Once again, the definition of an impulse function is delta t is equal to 0 when t is not equal to 0, and then minus infinity infinity delta t, the integration of delta t when t from minus infinity to infinity is 1. And then there are 3 different ways to use practical signal to define delta t with a limit. Now, when you multiply a function by delta t, so let's say phi t times delta t, this can be written as phi 0 times delta t. So that's, you have a function, phi t, and then you have delta t. Then when you multiply these two, this will become whatever the function had. Function has value for the function phi t has value for all values of t, but when you multiply that by delta t, that's just a function that is just phi 0. So whatever the value you had for that function at 0 remains, everything else wrong. Similarly, you have phi t times delta t minus t is called, it becomes phi t times. So again, this is phi t. The function phi t is, think about the function phi t as that, that function. This is phi t. It exists everywhere for t. But when you multiply it by delta t minus, if I have to draw delta t minus t, this is how I would draw it. T minus, sorry, this is t. This is t. It's t. So delta t minus t is that function right there. So delta t minus t with an arrow at t. So if you multiply these two functions that I just, function number 1, function number 2, if you multiply these two, what is resulting is going to be a function. It has only value here at phi t. It's slightly counterintuitive, but just think about it. Phi t delta t minus t, when you multiply it becomes phi capital T, because that's, this picture I just drew on the right explains why. So it's important. These two are important. We'll be using a lot. An example show that if so ut is minus infinity to t delta t. So if we integrate delta t, and then so it, this statement here is very intuitive, but it's also important that ut is, if you have to explain ut in terms of delta t, we can explain it as minus infinity to t, but because let's quickly see, right, draw a picture and see what that means. So where is that? So ut is this function. So ut is, so any values of t is equal to minus 10, t is equal to minus 5, 0, 1, 2, t is equal to minus 1, it is u minus 10, u minus 5, u 0, u1, u2, like that. U minus 10 is 0, minus 5, 0, 0, 1, and then it is keeps on going 1. Now, if you just think about delta t, just this, but the definition of delta t is 0 when t is not equal to 0, minus infinity to infinity delta t dt is equal to 1. So, and then what we are doing is we are finding minus infinity to t delta t dt. If you look at this integration, you can see that, so we are integrating from minus infinity here, but up to t. So now it depends on the value, it's going to depend on where the t is. If the t is negative 10, then t is negative 5, and then if the t is 0, and then 1 and 2. For each of, if you just move the t, and what is it going to be? If the t is negative 10, that integration is going to be 0. Negative 8 is going to be 0. At 1, it's going to be 1. Sorry, 1. Here it's going to be 1, like that. And then for if it is 0 at t is equal to 0, becomes tricky. So that's for that t is equal to 0 tricky part. We are taking this little bit formal approach to define that. But you see what is coming. It was 0 all this long, the integration of delta function, and after t it is going to be 1. So it is like a ut. That's ut. So yes, minus infinity to t delta t dt is indeed ut. But we need to, that when t is equal to 0, it needs to be formally derived. That's what we are doing here. So what we are doing, that is, we are defining a small function epsilon, and then we are saying that, so instead, we are just zooming in at that t is equal to 0 area. So that is what this picture shows. We are just zooming in area where t is equal to 0, and then we are defining an epsilon, very small value, epsilon. And then, so how this is going to happen? The integration is going to be 0 all the time. When you at the 0, what happens in 0 area? So, and then for that, we define an epsilon minus epsilon by 2 and epsilon by 2. And then this is how it's going to be. When you go from minus epsilon by to epsilon by 2, the integration is going to be 1. So before minus epsilon 1 by 2, the integration is going to be 0. After epsilon by 2, it's going to be 1. So, and then we will do that, and then we will put a limit for epsilon to 0, because that is when, that is how we define unit impulse function. So that's using the same way you can also explain this. Delta t is dut by dt. So most important thing is not this proof, but the fact that ut is minus infinity to t delta t dt, and then you can also write delta t as the derivation of dut by dt. So that's a very important fact, right? The delta t is dut by dt. There is, when we do some signal manipulation, that will be going to be very useful for us. So this sampling property and this multiplication property and this property will be useful for us later. Now I'm going to talk about some more functions. So even and odd functions. So what is an odd function and what is an even function? This picture tells the difference. On the left side we have even function. So even function is like a mirror. If you consider this a mirror, even function is exactly the same. So if you had something for t is equal to 10, you will have the same for t is equal to negative 10. Same here. Let's say this is sine cosine cos pi by 2. And then if you go to negative pi by 2, 0. So cos pi by 2 is 0, negative pi by 2 is 0. Cos pi is negative 1, cos negative pi is negative pi is negative 1. Sorry, cos pi is negative 1, negative pi is also negative 1. So, and then, so what is a good example of odd function? Sine. If you look at sine, if you go to sine pi by 2, it is 1. But if you go to sine negative pi by 2, that is negative 1. So that is the definition for odd function. So I had a small, I should call it FO, right? So it should be FE. E stands for even, FET is FE minus T. And then FOT, odd function, is minus FOT. So, minus FO minus T. So when T becomes negative, function also, same value, but negative. So look at the sine first, for example. When sine pi by 2 is 1, sine negative pi by 2 is negative 1. Same value, only the sign is reversed. And then this function right here is another example. So that is fx is equal to 1 over x, right? X goes to infinity. Is that right? What is the exact definition of the function that or is it minus 1 over x? Yeah, minus 1 over x. Yeah, this function is. So if you take a value here, x t is so I call t. So t is equal to 5, and then if you go to t is equal to negative 5, you will have exactly the negative value, whatever you had here. So if you had some value here, the opposite sign, same value there. These are very symmetric functions, except they're reversed in sign. So that's odd and even function. There are some properties about this. When you multiply functions, even function times odd function is going to be odd function. Even function times even function is even function. Odd function times odd function is even function. So very similar to when you multiply, when you multiply plus times plus, it's going to be plus. Plus times negative, it's going to be negative. Negative times negative is plus, very similar, but no relationship. But you have the same kind of pattern. That is, even times odd is going to be odd. So odd is like negative. Even times even is going to be even, and then odd times odd is also going to be even. So there are examples in the homework. You should try them. And then so here is important. Every signal can be broken into sum of odd and even signals. So if you just think about ft, it can be written as half ft plus f minus t plus half ft minus f minus t. If I just sum this up, it's going to be half ft plus ft plus half f minus t minus f minus t. It cancels and it is just ft. Same function ft, but we wrote this in a way that it looks two portions. Half time this and half time this. If you add them, what you will get is ft. But the important part is the first portion, phi et, half ft plus f minus t, acts like an even function. It is an even function. We will show that it is an even function. The second portion, phi ot, that is half ft minus f minus t, is an odd function. So that's all you have to do to prove is, you will substitute negative. So here, phi, let's take the even function. So even function is, the even portion of the function is what? Phi et is ft plus f negative t. Phi minus et, phi minus et is going to be f negative t plus ft, which is again same, phi et. So that is an even function. Similarly, you can show that the other one is an odd function. All right. So we have 8 more slides. I'm pretty sure we can finish it today. I want to finish it today so that you are ready to do the homework. There are a lot of homework questions, but you should do it because it will help. Because this is the basics for Singers and System, lecture 1. After lecture 2, we will kind of take off, and you will, if you don't want to feel lost, do all the homework questions, and for additional, I would suggest reading the textbook also. That way you'll be well prepared, because this course can, a lot of people say this is difficult. I don't want you to say that, because it is not a difficult course if you start early and really follow all this being taught here. If you understand everything that I teach here, there's no reason to say that and regret at the end of this course. But I can give a warning at the start that this, you have to work every day, not like, oh, I will study for exam. This is not that course. The programming course last time, maybe, but not this one. Well, doing well with this material will lead where in a person's career? That's a philosophical question. Whatever you do, we just do it well. This is the basic fundamental course for electrical engineering. This is the first electrical engineering course for you. This will open the door for electrical engineering. So if you want to become a good electrical engineering, you need to do that. So it's like a step. This is the first step. To go to the next step, you need to pass the first step. Otherwise, where electrical engineering will lead you, a lot of places. It's like, it's the best time to be an electrical engineer. You think about all these companies, electric cars, and rockets, and all of that is electric engineering. So this is a good time to be an electrical engineer. I heard people saying from Ford and everything. It's almost like it is almost like a draft. The NBA draft. They will just go and find good players for their teams, and it is like that for electrical engineers. There are people looking to draft good electrical engineers. I can tell you that much. So yeah, that's a good time to be an electrical engineer. This is agriculture is real. Yeah, it has application everywhere. I actually had a since Windsor is an area for a lot of agriculture. I can talk a little more about but just think about a greenhouse. A lot of things needs to be automated. All these sensors and all they are looking for a lot of automation and there as well. So yeah, it has a lot of useful stuff. But you know, this is the thing. You know, it is not something that there's no magic part. You know, there's no magic part. You know, we have to end of the day, you will know what is best for you, but we can always give you the best knowledge in electrical engineering, and then you will know where to take it and be successful. But yeah, there are many ways you can use this. I can tell you that much. But this is the basics, one of the basic courses for electrical engineering. So, okay, so there's an example here. Example, ft is sine t times ut. First of all, always when I see a signal, I want to draw it, you know, but that's always a good way. So let's draw the sine t times ut. So sine t is this. I'm just drawing, I'm just sketching it without too much details, sufficient details. So this is sine t. It goes t sine t, positive and negative. But when you multiply sine t by ut, the negative part will vanish. So there's no more negative parts. That is sine t by ut. It doesn't exist for t less than 0. Now, even part of the signal is half time sine ut plus sine, you know, half time ft plus f minus t. So sine ut plus sine negative t ut. So that's, you know, what is slightly. So that is half. But somebody asked, will these lecture notes be up? Well, if you want, no, okay, wait a minute. I don't say this. So yeah, no. The lecture video is recorded. Let me see. Did I press record today? Sometimes I forget to press record. Okay, good. So the video is being recorded, but I don't think this writing, you know, whatever I write here is useful. I will put the lecture note. The lecture note is already there, and the video is already there. Unfortunately, I did not save this thing. I don't want you to put a lot of garbage there. You know, I don't think this is useful. You should just open the lecture notes and make sure you understand everything by yourself. If you couldn't understand certain things, go to the video and see an explanation and come back and make sure you understand it. So yeah. All right. So if I put a lot of things, you will be overwhelmed. So I'm always careful about that. I don't want to put a lot of stuff that are not really, I know won't be useful. Video is useful. Most importantly, my lecture note is useful. So everything in my lecture note you should understand. If you don't, go to the video, and then because I am explaining everything. And if you still don't understand, there will be tutorials. You know, there are only 6 labs this time, so which means there will be like gaps where there will be, not this time there's a second lab, but probably next week there won't be a lab. So in the tutorial, you can go to the GA and ask questions about the stuff. So half ft plus f minus t, right? That's the even part of the function. We just saw it, f minus t. So that will be half sine t ut plus sine minus t u minus t. So now you need to know what is u minus t. So if this is ut, u minus t is this. Mirror, we saw that. There are 3 signal operations. One of them is this inverse. So u minus t is the mirror of the signal. So sine minus t times u minus t is this one, the mirror image of the sine t ut. So the left part of the right part of the signal is sine t ut. The other part is again sine minus t u minus t. When you add them together, that is a signal. And look, that signal is an even signal. You know, we can, when we look at it, we know that that's a symmetric, and the values are the same for the negative value of the time. On the same way, the even part of the signal is here. So that is a, sorry, that's the even part of the signal, first one, and this is the odd part of the signal. When you add these together, that's a plus, big plus sign there. When you add these together, our original t sine t will come together. So what happens to the negative part? They cancel, you know, because that is the reverse for each value of time. That's the negative part of the signal, so they will cancel. And other important part is, since it's the half, when you add them, that becomes 1. So that's a nice example to illustrate that even an odd part of a signal. Sine ut is the same signal as just sine to. Is there a difference? There is a difference. There is a difference. Sine ut, I was talking about this. So this is sine t. It goes both ways. But sine ut is just the half of it. This is sine t ut. So this is sine t. This is sine t ut. That makes sense? Yeah. Okay. Systems. This is some notes. We will talk a lot about system in the next lecture note. But what is a system? Let's see what else is remaining. Just to so linear time invariance. So probably I should not finish this today. Or at least I should review it one more time. Anyway, yeah, I won't finish this because you can start the homework. Actually, there's not much left. So system is I mean, it is a very general definition. Usually we define a system like an input. You give an input to a system and it gives an output. Now, the best example is here. This RC circuit, which or we will revisit later. So this is a resistor, and then there's a capacitor. So you give a voltage here. Let's say you give a voltage VT. What happens? Let's say output is this YT, the voltage across that, or the current through the resistor. That could be an output too. So then that is a system. You give an input like a voltage, and then you see something as an output. So that's an example of a system. Then you can just take open air as a system. For example, you have a telecommunication tower, that transmits some signals, and then here's your cell phone. You are just receiving that signal. So what is the system here? This whole medium could be considered as a system. This system can add noise, or this system can attenuate the signal. This system can do something to that signal. So we send a signal from the tower, and when we receive, you had to pass through a system. That's another way of system. And this is a system, that man-made system, a resistor and capacitor. You could then these all system, most of these system can be defined using some equations. Like so that's where we are going with in the next lecture. So we will revisit this a lot. So there is a linear versus nonlinear systems, constant versus time varying system, memoryless versus memory system, causal versus non-causal systems, continuous time versus discrete time system, analog versus there are many ways to define systems. So this is like a very high level introduction to systems, but we will focus on one part of the system called linear time invariant systems. So that's this whole lecture is about linear time invariant systems. So but we will come back and define it and revisit it again, but this is the first time linear system is defined. So a linear system, so I kind of define what is a system here. So let's now see what is a linear system. The system that satisfies the following two rules are known as linear system: the superposition property and the homogeneity property. So the superposition property is called as additive property. Other one is scaling property. So what is additive property of a system? So this is a system, the same system. If you put C1 as an input and you get E1 as an output, and then you give C2 as an input and you get E2 as an output, and then if you give C1 plus C2, you will get E1 plus E2. That is the additive property. Now, scaling property is if you give C as an input and you get E as an output, you get K times C as an input, you should get K times E as an output. So if you multiply the input by a constant K, the output is also comes out multiplied by a constant K. And then that system is linear system. So it adheres to the additive property and scaling property. So that's linear system. So here's an example. Show that the shown system is linear. So ft is the input, yt is output. So where dy t by dt plus 3yt is ft. So this system, now even the system I did introduce here, this system can be defined by a differential equation. Why it's differential equation? Because when the capacitor fills, there's an integration involved, and that can be also you will study, or probably already studied in circuits, that that can be the time the voltage across the capacitor can be written using differential terms. So a lot of system can be defined using differential terms. And here is an example, one simple example. Here the system is defined using this differential equation. So we want to see if both of those properties hold. So we are multiplying the system by K1, and then so the system, when you give F1, when you give input F1, you will get input Y1. When you get F2, let's assume you get Y2. Okay, we want to see what happens when we give F1 plus F2. And then in more general term, what happens when we give K1 F1 plus K2 F2? What is expected is K1 Y1 plus K2 Y2. If that happens, then the system is linear. So that's what we are doing here. So we are multiplying this first equation by K1, second by K2, and then we are rearranging it. And then we find that when you rearrange it, it is in the form of d by dt of this plus c of that is equal to this. So this is the new input, K1 F1 plus K2 F2. That is what I wanted to see. So we are giving it as an input. Earlier input was F1 and F2. And then if you look at it, and then that is exactly in the form of that C is equal to 3 for that example. So it comes to dy total plus dt plus 3y total is equal to f total. F total is this. So we were able to show that those two conditions hold, so that system is a linear system. Now, as a counterexample, another system is given here. That's y is equal to a ft plus b. So this system, so when you do the same thing, y total is a times f total. Instead of b, you get k1 plus k2 times b. So that's why that system is not linear. So that's like, you can compare these two examples to understand a linear system versus nonlinear system, because by definition a linear system should be if you give C1 and C2 as input, if you get E1 for C1 and E2 for C2, C1 plus C2, you should get E1 plus E2. In general, when you give K1 C1 plus K2 C2 as an input, given these two, you should get K1 E1 plus K2 E2. So that's what we are checking. We checked here and it was the case, and we declared that as a linear system. We did the same here, but it did not work. So we are saying that's not linear system according to our definition. time invariant system, so it's defined by if you give ft as input and get gt as output, and then if you delay the signal by t, your output should also be delayed by t. So here we have a example. We have a system yt, ft is input, ft is input. Oh, you have a class now? Okay, I mean, I will quickly say that, just take this example, if you do ft is input and fat is output, and then the same concept, you just apply that, and if the output is delayed by t, if you delay the input by t, output is also delayed by t, and then that is time invariant. So that's the check linear versus check time invariant. There's a lot of example in the homework, please check that. One last announcement, that is I'm not sure what question that is. Maybe you have time for that to discuss that question. Also, you can ask. Maybe I can discuss that in the next class. So I think we have time for the homework, right? Question 7. Okay, since okay, let me quickly finish this and we can talk. So the time, yeah, there is a lot of homework questions about this. Do them, and then yeah, we will visit this again. Homework 1, question 7. Question 7. So the power of the signals. Okay, what is the question here? You have to find a power of a function that has sigma in it. How do you treat the sigma in the integration? Where is the sigma? Is it question 7? That is not related to question. Question 7, power signal. Show that the power of ft, where ft is d, k. So you had to use that Euler's formula probably to work on this, but it's just pure, pure math here. There's nothing, you don't need to worry about any of the signals. So it is like an integration problem. Just go by the definition of power. If you want, I can, if you can send me some of the question that you need to be, you need some explanation, I can ask the GA to cover it on the tutorial. Okay, all right. So I finished lecture 1. You can try all the homework questions. That's an important thing. And then we'll take it from there. Yeah. So let me know if you couldn't finish a lot of questions, because I wanted you to try all the questions and make sure you're comfortable with it. If you couldn't, let me know, and maybe I'll consider extending the time and maybe do a tutorial. But I will do the tutorial anyway later also, so that we are all good with this lecture before we move on to the next one. All right, everyone, I'm going to when we sketch graphs, what specific details are you looking for? Important detail, where it crosses x-axis, like if it is a periodic signal, what is a period, all the important detail you need to show. You don't need to show it like sketch it very accurately. It doesn't need to be for scale, but you need to show important details. You can just write it, okay, this is where the signal crosses, this is the period, and then things like that. All right, have a good week ahead, and then just want to remind you there's a quiz on Wednesday, and then we will start the next lecture on Monday. Okay.